Imagine, if you will, the most powerful force humanity has ever unleashed, a nuclear explosion. Here on Earth we have a very distinct picture of what that looks like. A terrifying spectacle of raw power. A brilliant flash, a crushing blast wave, a rising fireball. On Earth, blast, thermal heat, and fallout. The atmosphere writes the story. That iconic mushroom cloud climbs miles into our sky. But what happens if that device detonates in the cold, silent emptiness of space? Up there, beyond the sheltering blanket of our atmosphere, the rules are completely different. The stage is empty. There is no air, no ground, no water. The explosion unfolds in a vacuum. Sound does not travel. There is nothing to push against. The familiar signatures of a nuclear blast on Earth simply vanish. On Earth, almost half the energy makes a blast. In space, nearly everything becomes raw radiation. Instead of wasting energy on a shockwave, up to 80% pours out as X-rays and gamma rays. It pours into the cosmos as a torrent of pure, high-energy radiation. So why is there no mushroom cloud in space? That iconic shape is a product of gravity and air. When a bomb explodes near the ground, it creates a bubble of hot, low-density gas. Like a hot air balloon, it rises rapidly and sucks up vaporized dirt and debris. When it hits the stratosphere, it can no longer rise. The cap spreads outward, forming the mushroom. Its atmospheric fluid dynamics, violent, visible, and terrifying. In space, none of these ingredients exist. No air, no ground, no buoyancy. The explosion doesn't rise, it simply expands into a symmetric sphere of plasma. Likewise, the destructive shockwave we associate with blasts is absent. A shockwave needs a medium. You can't have a wave if there's no water. The destruction in space comes not from a physical push, but from an invisible bombardment. A pulse of X-rays and gamma rays. These rays travel unimpeded until they hit something. Anything in their path, a satellite, a spacecraft, an astronaut, absorbs that energy directly. It's a flood of energy that fries electronics and tears apart cells from the inside out. For modern civilization, woven together by orbital technology, a nuclear explosion in space would be a catastrophe. Satellites are our communications, navigation, weather forecasting, financial networks, and scientific eyes. These marvels are incredibly vulnerable, not built to withstand a nuclear environment. The first wave, an intense X-ray flash arriving in a fraction of a second. Surface layers ablate, solar panels shatter, antennas break, mechanical shock rips things apart. Even if the shell survives, sensitive microchips are overwhelmed and permanently damaged. In an instant, billion-dollar hardware becomes useless space junk. Fragments become lethal projectiles. High-altitude detonations also create EMPs, continent-scale surges of electricity. Starfish Prime, July 9, 1962, a 1.4 megaton detonation at approximately 400 km proved how real this threat is. It knocked out streetlights in Hawaii and damaged multiple satellites. The blast injected high-energy electrons into the magnetosphere, creating an artificial radiation belt that lasted years. Satellites passing through that belt were slowly killed. Degraded panels, fried electronics, mission failures. Today, with mega constellations, a single detonation could cripple global communications, GPS, and weather services. What would happen to a human being caught in a nuclear explosion in space? The answer depends entirely on distance. At 1 kilometer, instant vaporization, your atoms join the plasma. At 10 kilometers, heat boils bodily fluids and causes explosive disintegration. At 50 to 100 kilometers, fatal burns and CNS collapse from radiation. At 300 kilometers, severe radiation sickness, low chance of survival. First comes a blinding flash that can permanently blind. Milliseconds later, X-rays and gamma rays shred DNA. The central nervous system is destroyed in seconds. Unconsciousness follows almost immediately. Thousands of miles away, you might survive the initial flash, yet receive a catastrophic dose. ARS unfolds, nausea and vomiting, a deceptive latent period, then infections, bleeding and organ failure. Spacesuits offer virtually no protection. Spacecraft hulls help only marginally against gamma rays. Dense materials like water, polyethylene, or lead help, but only distance truly saves you. A detonation near orbit becomes a lethal no-go zone. Operations halted, missions scrubbed. For astronauts nearby, it is a silent death, delivered at the speed of light. The destructive effects don't end when the flash fades. A detonation leaves invisible, long-lasting hazards that can poison orbit for years. One major effect, creation of artificial radiation belts far stronger than the natural Van Allen belts. High-energy electrons are injected and trapped by Earth's magnetic field, a man-made hazard. Satellites passing through suffer cumulative damage. pitted solar panels, fried electronics, mission failures. Starfish Prime led to multiple satellite failures. Telstar, Peril, and others were crippled. Beyond radiation, physical debris is a killer. A shattered satellite becomes thousands of lethal shards. At orbital speeds, even a paint chip hits with enormous force. One collision causes many more, a runaway cascade known as Kessler Syndrome. Soon, low Earth orbit could become an impassable, lethal cloud of high-speed junk. Weather tracking, GPS, communications, services would blink out one by one as satellites die. It would trap us on Earth, a prison of our own making. A nuclear explosion in space is not only immediate destruction, it's long-term contamination that threatens humanity's future in space.